Our next speaker, Professor Talluri, Professor of Operations Management at Imperial College. He's also the chair, the Munjal Chair in Global Operations Management, Director of the Master of Science in Business Analytics. Previously, he was a research professor in the Department of Economics and Business at the Universitat Pompeu Fabra in Barcelona. He has a Master in Industrial Engineering from Purdue and a PhD in OR from MIT. He has been visiting professor at the Kellogg School of Management, Northwestern University, and has taught classes at Indian School of Business, Tuck School of Management at Dartmouth, INSEAD, Stern School of Business, NYU, and London Business School. His research interests are in service design and analytics, transportation and operational pricing of consumer goods and services. He is the co-author of the book Theory and the Practice of Revenue Management. He has published in Operations Research and Management Science Journal and is the co-winner of the Informs Impact Prize in 2016, the Lancaster Prize in 2005, the Pricing and Revenue Management Section Prize in 2004. Please welcome with me the father of revenue management research, Dr. Talluri.
Thank you. That's a bit of an exaggeration, father of, but thank you anyway. So that's not my talk. I want to thank Ibrahim for inviting me and the organizers for this wonderful conference in this wonderful city. Let's see. Okay. And my talk is a little bit different from Hamid's talk. It's going to be much more less visionary and more focused on a very small scale. It's on facility location decisions from public data, and let me explain how this research originated. It started off with this so-called Yelp data challenge, which I'm assuming you know what Yelp is. It's a consumer, it's a restaurant review site. It started off like this around 10 years ago. And then it branched out into other reviews, but primarily it's about restaurants. So consumers go to a restaurant, they eat, they come back and they say it sucks, it's actually quite very good, or it's the best meal I ever had, and they give star ratings. So on the left you see one of a typical review. It has some stars on the top, and the review text is below. And then on the right-hand side, you see a lot of attributes they give about the rest. Yelp gives you about the restaurants, like all these features, or what in statistics they call covariates. Now, this Yelp data challenge has been going on for 6 years, or 6 or 7 years, and the idea is to encourage research analyzing these data sets, and a whole bunch of computer scientists, students as well as faculty, they spend a lot of time analyzing it and coming up with research papers, and some of the winners are the ones you see below. So I used this data set in a class last April, and in a digital marketing class, and I gave this data set and I asked them to analyze it. And students, they came up with very nice pictures. I'll show you some typical ones on the next slide. And I looked at these research papers and I thought, what's the point of this? If you look at the focus of the research, it's on things like, how do I predict the number of stars people give based on the text of the review? Okay, that's the winner, for instance, the last paper. Okay? So that was like, is there all there is to this analytics business? Is it all this CS, technical? I mean, how can I explain this to a business guy that analytics is actually useful? So as Amir was saying, there's various versions of analytics. There's descriptive analytics. There is what's it called, the prescriptive analytics, and so on. So descriptive analytics, the way I see it, are nice pictures. Okay, so you get some very nice pictures like this, and this is my students' work. So all you need is some Python mastery and knowledge of some graphic tools, and then you can get pictures. You map it on. You can do this even on things like Tableau. You map the distribution of star ratings for Mexican cuisine, Thai cuisine. It's quite. Give them 1 hour, they come up with all these pictures which are insightful. I mean, they tell you, for instance, that most of the restaurants are concentrated in a few zip codes, and this is Las Vegas actually. So it's not hard to imagine where the zip code lies. Okay? It's a central strip where all the casinos are. You can look at what are the distributions of cuisines that people in Las Vegas like. Well, it's not too surprising. It's American. Okay? And then comes Mexican. You do it in Edinburgh. Turns out to be British and the curry houses. Okay? So, so things like this. What is the distribution of the star ratings across restaurants? You'll see that the last one, the average of all ratings tends to be concentrated around 5, and then it sort of slopes down all the way down to 1. Okay. So we wanted to take. So this summer, my PhD student Muge and I started asking the question, but how do we make this useful? And useful not in a global sense and like solving the hunger problems like Amir was saying, but more on there's a single firm and it wants to use the data so that it can make a business decision. Okay, so it's a very modest kind of goal, but hopefully a lot of businesses will find these kinds of questions useful and it will have some impact. So here's our goal. Like, you think of a restaurant chain which is a big company, or even like a single small mom and pop kind of firm, and what they want to do is to make a decision on where is the best place to locate a new restaurant. Okay, so what the exact location, as close as possible to like latitude and longitude, and also what type of restaurant would be successful. Okay, what kind of cuisine? Let's say they're flexible, they have access to talent, and what features will maximize the profit. Okay, so you saw this list of features at Yelp, and which features to choose. So what in operations research terms, what this is like a product design problem. Okay, so or a product line design problem. Potentially, you can also look at multiple locations. If I have to locate K restaurants in a particular region, what is the... so these are actually classical facility location problems. But the difference that, or the value that we are going to contribute with our innovations is make the model richer using big data or cross data, let me call it. And also build models which are based upon our new data that we have access to these days. Okay? So this, in operations research, this kind of problems are called maximum capture problems. There are quite a few papers on this. People actually try to model it, try to solve it, and I'll come back to it later. Okay? So what kind of data do we need? Well, there's another self-imposed challenge that we put on ourselves. We are not going to pay for data. Okay? So this is like going to be a small firm, and they're interested only in free data. Okay? And it turns out, after some little bit of research, not too long, there are actually quite a few data sets which can be potentially useful. There is, for instance, our original starting point, the Yelp data set. There is a NASA data set which is freely and publicly available, which gives you what is the density of population at a very, very fine range. And we're talking about a range which is less than 1 square kilometer. Okay, so it's like 0.7 by 0.9 kilometers. Okay, so it's 700 meters by 900 meters. There's a factual API, and this gives you the number of hotels which are located in every city by latitude and longitude, and also how many rooms the hotel has. And you might be wondering, what do hotels have to do with restaurants? Well, because we want to estimate what is the transient population in a city like Las Vegas, because I have a lot of tourists. So we use that to estimate what is the number of tourists that you can expect in every grid. Okay. These are small grids. Google Maps API, which is, as you can imagine, going back from latitude, longitude to zip codes. There's an Open Table API, okay, which is a restaurant reservation service. It's not public data, but we can sample the API because they allow a limited number of queries. And what we want to do is to sort of correlate the restaurant reviews, the quantity of restaurant reviews, how many reviews a restaurant has with how many bookings that they actually get. Okay, this actually turns out to be quite tricky. We have Craigslist, from which we download what is the cost information, how much does it cost to open a restaurant based on the rental rates in that zip code. We have IRS data, which gives us the income of at a very, very micro level. Okay? And finally, we have demographic data directly from the US Census Bureau, okay, which is the age, the income, all these things. Okay? So you might imagine that a small grid around American University, which is full of student population, they might not be interested in a Michelin 3-star restaurant. They might be more interested in McDonald's. They might be interested in a kebab joint. So this is all the free public data that we were able to gather from a huge number of sources. And I want to mention that some of this data might be, you might say it's a little bit outdated. Like census, for instance, they take it every 10 years in the US. There is supposedly more current data like ESRI, but you have to pay a little bit for it. It's not a huge amount, and potentially a business can pay for it, but we chose not to use it, okay, just because we want it to be free. And this is like a perennial problem we face with even paid data. So we pay for this ESRI. What we were not sure of is how good is this data. Okay? How are we going to validate that these guys are actually reflecting the reality demographics? Okay? I think that's an unexplored area with all these data sets. So these are the pictures. This is the population density of Las Vegas, huge. There are around quite a few zip codes, okay? And around, if I recall right, around 100 or 150 zip codes. And you can't really see the colors here, but this is color-coded. Okay? And as I said, these are the various reasons why we use these disparate sources of data. Now, despite all this data, there's tons of data that we couldn't have imagined gathering even like 5 years ago. Turns out that the data that we really want, that we would really need in order to estimate and optimize these decisions is not available. And I don't think it will ever be available. Okay? Take some simple thing like what is the demand at a particular restaurant? Okay? And that's almost impossible to get. Okay? You can only estimate it very crudely, or you can use some other indicator to estimate it. And I think this is going to be a perennial problem because a restaurant, because this is strategic data. Okay? This is internal strategic data of companies, which you really need for making these operational business decisions, and you can never expect to have it. What this means is that at some point or the other, we have to rely on models, and modeling is as important as just gathering the data. Okay? With the right model, with the right parsimonious set of parameters will actually turn out to be quite good. So we build models, and we need a couple of models. We need a location model and also a customer behavior model. Okay? And of course, both of these are going to interact. So the idea is that red dot, the city is divided into these grids, which are very, very small, okay? Within a few. I have a new fan. And put her in the front seat. Interested in big data. So the red dot is your potential location in the grid, and the grayish dots are all the existing restaurants of different types. So customers are distributed across the city. Different grids will have different densities. And what the customer does is, at a random date, they decide, look, I want to go and eat out. Okay? And they decide based upon the cuisine type that they're interested in, as well as the distance from where they're located to where the restaurant is, which restaurant to visit. Okay? So as you can imagine, you're not going to travel 5 kilometers to visit a kebab joint, but you might very well be, if it's a Michelin star, maybe you will be interested in it. Okay? So it all depends upon distances. It also depends upon the quality reputation of the restaurant. Okay? Now, the customer visits the restaurant, and once he or she visits the restaurant, they eat, and conditional on the visit, conditional on the fact that they visited the restaurant, and this is the first-time visitor, they rate the restaurant. So we need a model on how the ratings are created and also how the customer visits the restaurant. Okay? So that from the data, we estimate these parameters, and I'll show you later the numbers. We have M sub Z is a total population in a zip code, and this we get this from the census data. We distribute this data according to the density in the small, tiny grids based upon the NASA data. Okay? And we calculate distances between each grid based on their longitude and latitudes, which is quite trivial. And we have the restaurant locations, pinpoint locations by exact point where they are. And our model for how customers visit, okay, well, the total demand for a restaurant which is located in a grid G, okay, well, let's say the center of the grid, is given by the population distribution in each one of the grids multiplied by some probability of visiting the restaurant. Okay, so it's for every grid, they flow to the restaurant according to this logit formula. The logit formula, as you can see, is a function of the parameters of the these are the parameters of the customers in that particular grid. What are the demographics? What are the age? What are the income? And we have only probabilistic information here. The rating of the restaurant J, and there's a gamma is the weightage they put on the rating, and the cost. Okay? So distance is the cost of going from J prime to J. Okay? So these are the various. So it's just like a standard logic model. The second model that we need is how these ratings are created, and here we use a kind of Netflix kind of model. Now, those of you not familiar with this, I mean, we all experience recommendation systems, and this is the famous Netflix prize, and they have a big problem with this. So let me briefly explain to those who are not familiar with it what the model is. So Netflix has a problem that they have users or the viewers which are on the column, like let me call them Mo, Larry, and Curly, and there are a bunch of movies: Batman, Superman, Rain Man. And Mo has seen Batman and he rates it at 5, rates Superman at 4. Larry has not seen Batman but rates Superman at 1. He has seen Rain Man at 3, and so on. So it's a matrix where the rows are the users and the columns are the movies. It's a huge matrix. It's also a matrix which is very, very incomplete in the sense most of the users have seen only a few movies. Based on this matrix, what Netflix does is it comes up with a recommendation for a particular user on what is the best movie for you. Okay? So they've been struggling with this problem for many years, and some of you might recall this Netflix prize where they said, look, we'll give you $1 million for anyone who can improve the predictions beyond what we are actually doing. And some of you might remember the performance of, there's like thousands of teams which participated, because 1 million is a nice big figure. It attracted a lot of attention. It's a precursor for all these Kaggle prizes that you see nowadays. The performance was pretty flat for a while, and suddenly you see like a qualitative jump. Okay, so there's a significant jump, and there's some inflex point there, and why? Okay, well, turns out there was a new model. And this model was this, what I call this P transpose Q model. People also call it the latent factor model or the low dimensional matrix completion. What they say is there are a bunch of latent factors for every user that we cannot observe, we cannot even quantify, we don't know what they are, but they are there. And likewise, there are exactly the same number of K latent factors for every movie. And the rating that a user gives to a movie is the interaction between the user and the movie. Okay, so P transpose Q. And our goal is to estimate this P transpose Q from the incomplete data and predict the rating. Okay, so this is, by now it's pretty standard, hundreds of Python packages which actually do this for you. So the idea is I have an incomplete matrix, and what I do is I estimate 5 is equal to P more times Q Batman, 4 is equal to P more times Q Superman. Okay, so I have a bunch of equations. There's a theory from matrix theory, there's a singular value decomposition, which is like an inspiration, but it's not really applicable because it's an incomplete matrix. So what they really do is like a least squares fit. It's penalized least squares, and it's not convex, but it behaves quite well. Okay? Now, there's some difference between this. No one has really applied this to a Yelp data set in its standard form because there are differences. In a ratings data set, we don't really have individual users' ratings. In the sense, most users, they rate only one restaurant. So it's not very useful. You cannot, and we don't really want to predict user-level ratings. We don't want to say, how will this person rate this restaurant? That's too fine, and we cannot hope to predict it accurately. And what we model is, we have a ratings distribution. And the ratings distribution, I'll show you some how these distributions look like in a minute. And our model is there's a ratings distribution, so R is a random variable. It's given by the restaurant features, restaurant characteristics, plus some random distribution P multiplied by the restaurant features. Okay, so it's like a probabilistic version of the Netflix model. Okay? And we still have this two-part model that customer features do not really affect his rating as such. Okay, so the X, the customer's demographics and age, they influence the fact that the customer goes to the restaurant. Okay? But once they're at the restaurant, these latent factors only capture the taste and the quality. Okay? What is the individual taste and quality? So the distributions of ratings, you see, they tend to be highly skewed. Okay, so they tend to be very much towards 5. They tend to be concentrated around 3 or 4, and then or they very rarely you actually see the one on top. Okay, that's an extremely bad restaurant. Okay, but these are very, very rare. Most of them tend to have a distribution like this, or they have a peak around 4 stars or 3 stars. Okay, 99% of the restaurants will have the second and third kind of distribution. Okay. So what we want is what is the right distribution for the ratings, and we would preferably like something which can model skewed distributions, not a normal distribution. Okay, normal would be terrible because it's very, very symmetric. We want a skewed distribution, we want it to be discrete, we want it to be flexible, and most importantly, we want it to be very easily estimable. Okay, we don't want something which has like 10,000 parameters, which is hopelessly difficult and not reliable. Okay? So it raised some interesting questions on singular value decompositions for random matrices. I mean, they're still quite unanswered for general distributions. So what we did was, just for tractability, is we used the Poisson distribution for modeling these ratings distributions. And if you recall from probability classes, the Poisson distribution is actually quite flexible. It's skewed. Okay? And most importantly, it has a single parameter, okay, which is a huge advantage. Okay? So you can model also, this is a rating distribution which peaks at 4. This is a rating distribution which peaks at 3. Okay? So it's quite flexible. So our distribution model is that the rating comes from a Poisson distribution with our B transpose Y plus this P transpose Q of latent factors. Okay. So we estimate this, and there are multiple options. These are design decisions almost on how to fit a distribution with a ratings distribution. One could potentially use fancy methods like the KL distance metric or the chi-squared. In this particular case, we just use a simple method of moments. So we just match the mean of the Poisson with the mean of the ratings distribution. And these are some of our results. So this is estimation with no covariates. These are, for example, some features that each one of the restaurant can have, and this is the weighting. And here's another fit. I have only a few minutes, 5 minutes maybe. Yeah. Okay, I have 10 minutes. Okay. Yeah, okay. So this is a this is the same estimation where we have multiple features that we included in the model, and most importantly, how well does it predict the ratings? Okay. So here, for example, this is a sample output on the this is on the test data. So we have, I mean, like all good modern prediction methods, we divide our ratings into a testing data and a training data and a test data. So we estimate based on the training data and we predict on the test data. And here are some examples in one grid point. Okay, so this is the actual rating 3, and our model predicted 2.8 is the prediction for this one based on the features. We have the burger restaurant. This is quite close. You know, some of them are not so close, but still it does a fairly good job, the whole thing. Okay. So based on this, so it's a two-part estimation procedure. So the first part, we predict the ratings. If I locate this kind of restaurant in this grid point, what rate? Yeah, 2 minutes. Okay, the miscalculation. Okay. And this part is we estimate the parameters of the logit model. Okay, so remember that the first part is customer decides to go to the restaurant. Okay, so what are the parameters of this decision? And the second part is once in the restaurant, what will the customer's rating be? So this is an estimation procedure, but then we come to the final part, which is what do we do with all this estimation? Well, like any good operations management or operations research, we want to make it operational. And what we do is we put this into a mathematical program. It's actually an integer program. And this is, so, I mean, this is not that original because this is similar to what people use in the maximum capture problem that I mentioned before. So people have thought about this. It's a very, it's not an easy integer program, but solvable by modern packages, let's say. So the final slide, what is our contribution in this research? So we took I mean, it's almost like an exercise in taking data on the web from multiple different sources and building an operational model. We improved traditional facility location models because if you look at this maximum capture literature, they formulate the problem, but they don't even bother about estimating it. They just simulate some data based on some parameters, solve the optimization problem. It's not something that I would actually base my decision on, but what this data and this analysis and this prediction makes is that makes the model some sort of, gives confidence in the results for the end users. And we also play around with this classical latent matrix factor methods so that they're more realistic, they fit some sort of rating distributions rather than individual user data. Okay, so that's the end of my talk. If you have okay, that's great. Thank you very much.